Yeah, I want to talk about machine learning approximations to the exchange and correlation potential in density functional theory. I will start, because I'm sure I'm going to run out of time, acknowledging the people that did the work, which is mostly all due to my student Sebastian Dick, who graduated a bit less than a year ago, and now it's been taken over by my other student, Alec Wills. So again, because I do have actually quite a packed talk, I'm actually not going to spend a very long time on the introduction, mostly also because I think we've had enough introduction about density functional theory. What I will say is that basically what we are going to be working on is within the framework of Kohn-Sham density functional theory, which is, in theory, an exact framework and an exact ansatz to calculating the total energy of a many body interacting electron problem mapped into a non-interacting electron problem in the presence of an external potential. And so we reduce all those the calculation of the correlations in the wave function to the approximation of an external exchange and correlation potential. And so what I'm basically going to be talking about is different methods to do this approximation. But I also want to actually motivate what we do from a more physical point of view. So let me start saying something that I think already, again, has been repeated very much throughout the workshop. Of course, that our density functional approximation is basically uniquely defined by this integral in here. If we know the density, the exact density in the ground state, and we know our exact energy exchange and correlation energy density as a function of the density and other parameters of the density, as we will see, well, then we solve the problem. Now, of course, the issue here is that we do have the complexity and the null locality that we keep on including in this exchange and correlation energy determines the expense and also, of course, the accuracy of our approximation. Ideally, we want to be there in the heaven of chemical accuracy, of course, but this is what we end up doing, especially, and I'm really not coming from the community of developers of exchange and correlation functionals. Indeed, I feel a little bit like an elephant in a china shop, and I actually feel I want to apologize to the owners of this china shop. Some of them are in here, so Kieran and Andreas, because I really don't come from that theoretical development of methods. Instead, actually, I entered in here driven by the need of the applications to actually find more accurate methods. And indeed, when I say what we end up doing is that we are really simulating rather large and complex systems, which you could say they are not strongly correlated systems, and that in principle are well described at DFT, but still we need an efficient method to compute not only the electronic properties, not only the total energy, but also response functions to the density of the system. And so, of course, this is what we end up doing, which are approximations that we can relatively easily compute. And what we do in small doses is include higher ranges, so, of course, hybrid methods. And this is what I usually had. I think this might be obsolete after Sandeep's talk. Or Sandeep, is he? Okay. So it looks like we are going to be able to very efficiently calculate exact exchange, but I'm going to assume that that's actually not the case. And actually, I do want to make a parallel, I don't know if there are any climber in the room, sort of climbing up this ladder is basically exactly the same that happens in real climbing outdoors. This is what we would like to do, but this is what we end up doing. So I'm not sure if there are any actual climbers in the room. Now, there's also Kieran this morning actually mentioning, not only Kieran, actually many others, that, of course, in practice, even though what we want to look is for a universal DFT approximation, in reality, there is not one single DFT approximation, but there are many. And then, even though each one has their favorite choice, at the end of the day, when we actually make a choice, what we do is sort of play by trial and error. We look for the functional that better fits that data. And so indeed, I mean, some of these alphabet and names might be familiar to you, some others are not. And indeed, depending on the system you want to study, you will choose one, other. In the case of oxides, I don't know how many of you know the Wu-Cohen potential, probably not many, but actually it's a rather common exchange and correlation functional in the description of oxides. The bio community has their favorites. And then, of course, if you have a new system for which you don't know what to do, well, how to choose, well, you read the literature, you see what other people do, and you choose that functional. So that's the standard approach for those of us more on the applied side to how to choose that approximation. And so as I say, I come actually, when I started in here, I was, and I'm still, doing a lot of work on trying to understand the physics on water using first principle simulations. And so of course, everybody knows that, oops, there we go, that water has an unconventional phase diagram that has many anomalies. Probably the most famous one is the fact that ice floats in water. And you look at its phase diagram, the one that basically we learned from high school all the way to the end of our physics or chemistry degree. That will be the standard phase diagram of water, your triple point, your critical point, gas phase, liquid phase, so on and so forth, depending on the slope that you have in here. Indeed, for water, you should have a negative slope here. That negative slope indicates the fact that the ice floats in water. But in reality, actually, is a much more complicated system. Indeed, this is an area of intense research. And questioning, or the proposal is that indeed there is a second critical point in liquid water, very similar to what David has been telling us this morning on hydrogen, which is such a simple system and still has such complex phase diagram. Water is another one. And indeed, the existence or not existence of this second critical point is under strong debate. So why do I bring it in here? Well, I'm bringing it in here because indeed, if this critical point exceeds, that will mean actually that liquid water at ambient conditions is what is called a supercritical liquid, and a supercritical liquid which is rather close to that criticality point and manifests in the fact that you will see a fluctuation between two different liquids, a low-density liquid, which comes from a low-density amorphous ice phase, and a high-density liquid, which comes from a high-density amorphous ice phase. What you're seeing here is that first-order phase transition that occurs in between these two ices. And the problem of this critical point is that it occurs in the so-called no man's land, which is a region that cannot be accessed experimentally. Now, I'm not going to talk about the physics of this, but what I want to say is that indeed that supercritical behavior, even though water is a system that is really non-strongly correlated, yes, no local van der Waals correlations are actually very important, still is extremely difficult to describe by DFT. And when you look at all the different exchange and correlation functional approximations, well, they all, and this is, by the way, already in the so-called thermodynamic limit, and give you a different description of both the structure and the dynamics. And so the question is, it's not even clear what is the best, or even for, I mean, these are all approximations up to meta-GGA, but even for hybrid functionals is yet not there at the experimental level. Now, all these simulations, I just want to make a note that they were done following the same sort of path that David described this morning. So they are done with neural network potential, DeepMD, which is fitted to reproduce DFT. And the reason for that, actually, Juan Carrasquilla, in his talk yesterday, he actually pointed out how the exact sampling from an approximate distribution is better than an approximate sampling from an exact distribution. And so here we are sampling for that approximate distribution, which is very, very close to the exact one, and gives us an insight to basically know the actual quality of our exchange and correlation functional. Now, so the thing here is that if you look at what is the state of the art of our exchange correlation functionals, and these are just mean absolute deviations or energy errors for different functionals, as compared, I think the reference here, I'm not totally sure if this was done with quantum Monte Carlo coupled cluster. But bottom line, what you see here is that the errors are very large, and the one that performs better is MB-Pol, which is actually a force field which was fitted to reproduce coupled cluster SD single, double, and triple energies. And actually, it's a force field which is actually, well, here I say it's more expensive than traditional force fields, but it's still an order of magnitude cheaper than DFT, and it's doing much better. So when we started working here, we really questioned, like, well, if that can be done with a force field, DFT should at least be able to be as good as a force field. And so that's where we started. And so what we are going to do is, as I say, I'm gonna follow a path which is sort of gradual of, this is still not, well, it is machine learning. Any fitting that you do with your computer is actually machine learning. And so I will claim that this is machine learning. It's not modern machine learning, but actually gives us a lot of insight on the things that we are gonna need as ingredients for the future machine learning path. And so what we are gonna do is a delta approach in the training. We're gonna look at what is the change in exchange and correlation energy that we need to reproduce some set of given reference energies. And our set of reference energies in here are going to be exactly the same that were used by MB-Pol. So in a way, we are actually saying, if this force field was so good, we are going to repeat what they did, but within the DFT framework. And so, so we are going to make an assumption, and this assumption is it can be large, but as Kieran pointed this morning, in reality, it's not that bad, which is we're going to assume that we're going to start with a baseline functional that gives us a density that is very close to the density that will be reproduced by the reference system. That is an assumption, of course, and I'll talk a little bit more about that. But we start with that, and we're saying that, well, my total energy, I can decompose it into everything that doesn't depend on the exchange and correlation energy. I have my baseline, which is a given functional that I choose to start with, the one that actually gave me these densities, and some correction that I need to apply to obtain the exact reference. And so if you write now what we want to do, again, in the language of DFT, remember the integral that I showed you all, this is all what we need for our exchange correlation approximation. Well, what we need is a density and some model for the energy density as a function of whichever parameters. We're going to remain within the GGA approximation, meaning that we are only going to make it dependent on the density and the gradient, but we're going to make a transfer of variables where we, instead of density and gradient, we're basically using KF, KG. Basically, the reason for this, of course, is that it's giving us a much more uniform space. They are both, they have the same dimension. They are both momenta, so dimension 1 over L instead of density and gradient, which we have span different scales in absolute numbers. And so all we need to do basically is express that density in this new space, and of course our natural variables for this energy density. So usually this is the way you are used to seeing your densities. This is just an isosurface, so in real space, of course. Again, will depend on what's the nature of your system, in that this dimension of this box will depend on the dimension of what the atomic coordinates of your system or the extent of your system. However, when you make this transformation of going from density and gradient to KF, KG, so this Fermi momentum and this gradient of the density, normalized gradient of the density, you come here where actually now everything is much more uniform. And indeed, I could have one water molecule, I could have 100 water molecules, and still they will map to something that looks exactly, not exactly, but approximately like this. So now I have something much more uniform. And what we are going to do is actually something very, very simple, which is just saying, well, let's get our exchange and correlation energy. So this is what we want to do, and we're going to simply parameterize with some set of parameters, and in terms of some interpolating functions, which you can choose any type of simple interpolating functions. And so now all what I have to do is solve for this problem in here, where these are going to be basically my exchange and correlation and energies for every set of data points. So n indicates here which system I'm looking at, which model I'm looking at. Now here I'm already taking it as the delta. Okay, so this is the reference energy minus the baseline plus the minus the total energy of the baseline plus the exchange correlation part of the baseline, basically to avoid the double summation. And so what all you have in here is basically a projection. It's basically a projection of my data, which is in here in the parameter space, and my parameter space is the parameter of the energy in this subspace of Kf and Kg. Now in practice, of course, and this is what, with that, that's all what we will need to do. So if we parameterize that and we invert this problem, we will find a set of parameters, and that will give us a model for my exchange correlation energy. In practice, in reality, we are not going to do that because we still want to remain within the framework of a standard GGA, where basically with our exchange and correlation energies is expressed as the LDA, the homogeneous electron gas exchange and correlation energy times an enhancement factor. And even more, and this is another very big approximation I'm making, is that I'm going to assume that the correlation part is fixed. I'm going to fix both the local and non-local. There's local and non-local correlation, but the vast correlation. But I'm going to assume that they are fixed, and the only thing that actually my model is doing wrong is the exchange. And so now makes it much more easy because this exchange is basically expressed because of scaling laws. We express this exchange enhancement factor as the reduced density gradient in here, so a single parameter. And so at the end of the day, basically what we are looking is a specific parameterization of this enhancement factor as obtained from the projections that I showed you in here. Okay, so that's what we do. We can add regularization, and indeed, we need to add regularization because we want to impose constraints. And so basically, we could just minimize a loss function that takes into account the errors of the calculated energies and the estimated errors of our parameter space. But by doing this, actually, it is very hard to encode constraints. Now, Kieron claims that it's not necessary to impose constraints. I will say that in this case, it's extremely necessary to impose constraints. I want to show it to you. If we don't impose constraints, what we'll get is enhancement factors that will deviate from the very largely from physical the characterizations of the density. And so the natural way to do that is including imposing a Basin optimization, which is actually really simple. And I will go through it very, very quickly because it actually motivates also what we'll be doing later. So what we are going to do is actually maximize this Bayesian probability of finding our parameters given the reference energies, which is proportional to the probability of obtaining those reference energies if our model is correct, times some a priori estimation of the probability that our model being correct. And so what we are going to do here is for the first one, we just said, well, for both of them, we'll assume Gaussian probabilities. And this one in here is basically easy to estimate. That's just, we'll include here the errors in the energy, which are due to, not to the functional itself, but to all the other numerical approximations, so an estimation of our numerical errors. Whereas for this a priori estimation of our probability or the accuracy of our parameters, we are going to basically impose that they do not deviate from the existing exchange correlation functionals which have been developed already. Yes, sorry.
Can you elaborate on what the delta En what kind of numerical errors are important for you?
So for me, I have, there are many. So of course, there's basis set error. There is a grid, real space grid error for my integrals. There is the tolerances that I'm having on the self-consistency calculation. So all of those, even the pseudopotentials you
Those are all deterministic.
Correct, and that's
They're not really probabilistic.
Well, yes and no, but of course the fact that they are deterministic, but I am basically trying to get, I want to filter those errors from the actual, from energies which were in principle I'm taking as exact. So that's the main idea. So yes, and I'm not really taking into account that I'm really not, I guess, in a way, I am within a given error for those approximations. So yeah. Okay. So if you look at actually the covariance matrix, so the covariance matrix is written here, which is basically the covariance matrix of a set of all, well, of a large set of previously known GGA functionals, were expressed again in our parameter space. Remember, where parameter space now is much reduced is the reduced density gradient S. And what you see is that it is very highly non-diagonal, meaning that all those functionals are correlated in a very, very non-trivial way. And so maximizing this probability is equivalent to minimizing a loss function, which basically contains this information. And so we minimize this with respect to the functional parameters, and that naturally will impose the constraints that all these other functionals are somehow imposing. So just very, very quickly, what I do want to show two things. Again, this is very similar. This is not a density in this parameter space, but it's a change of density in this parameter space for a water monomer as it changed from going from the experimental geometry to the underlying method geometry. In this case, it was with van der Waals CX. And one thing that you're already noticing here is that these changes are actually perpendicular to the lines of constant S. And remember that my exchange enhancement factor is, actually, I'll put it in here, which is easier. So it's Kg over Kf, and which says that these changes we really won't be captured by any change in the exchange enhancement factor because precisely they are perpendicular to that constant ends changes. So it is already saying that basically that optimizing this functional to reproduce the correct monomer geometry will force the functional to undergo very artificial changes based on changes of this density to achieve that bond construction. And those artificial changes I didn't show in here. If I don't impose constraints, you'll see very quickly that you'll see very large oscillation on your enhancement factors. So what happened is that we realized it's impossible. It's impossible to optimize the geometry of the monomer and at the same time optimize the intermolecular interactions of water. So what we did is we say, okay, the monomer can actually be included as an ad hoc correction, and I won't go into details how that is done. And then we just optimize the long range and semi-long range interactions within the exchange. And then you get a functional which is actually very close to MBPOL, which is what we had. But it's really non-real. I mean, it's non-satisfactory. It was good as a proof as a fact, but it's not a functional that you're going to want to use if you need to correct for the monomer. And so what we learned is that, of course, this GGA functional form is too constrained. It doesn't allow for independent changes on these parameters. It is important to impose these ab initio constraints in the functional optimization, and we did learn a lot by doing the data analysis in this parameter space. Now, one thing very important is that we learn on fixed density, so assume zero density errors in the functional, which is obviously wrong. Okay, so all this to say is that doing what we were doing is a good exercise, but it's not the right way to go. We need much more flexibility in the functions that we're going to add to modify our functional, and that's where neural networks come in. So The non-locality of the extension correlation functional is something that we actually need to include, even if we do a GGA approximation, which is semi-local. If we stay fixed on the natural form of following just the development of an exchange enhancement factor, what we've seen is that it's not gonna take us very far. And so we can do two things, and these are the two methods that I will present. And so in one is deviate, going completely a different route from having an exchange and correlation functional, which is defined as in here, basically have an exchange correlation energy density, which depends on given parameters. And instead, we're going to go to this other approximation where we're going to take a density, and we're going to a baseline density, which already contains a lot of the physics. If you want the baseline physics, I mean, I will say that density probably takes you already as far as probably 95% of the correct energy. We saw anyway this morning that the correlation energy is a very, very small part of the total energy. And so by doing that, the information that is in that density can still be very useful to learn what are the variations that density could give us to improve on the exchange and correlation energy. And so we are going to start with that, this neural XC. So we still delta learning, and you'll see as before, but we're going to end up a functional which is sort of a global in that, I mean, the neural XC functional is a sum of these two, and we'll have a potential which is a sum of these two. So let me start. So what we are going to do is we take our electronic density from a baseline DFT calculation. We're going to project over atomic descriptors which are center of my atom. So I'm projecting onto a set of orthogonal atom-centered basis functions. Now, these basis functions are species dependent, and I'm doing that because I'm going to build a neural network, and indeed I'm going to be within the Wheeler-Parinello architecture. We choose to have atom-centered neural networks to achieve permutation invariance on our system. Still, of course, so Wheeler-Parinello choice gives us the permutation invariance. We still need rotational and reflection invariance, which basically is achieved by projecting onto these atom-centered basis functions, which are products of a radial function times the spherical harmonics. And so these coefficients in here are the coefficients of those projections, which are then can symmetrize. So the spherical harmonics can be symmetrized. The sum of the square of these coefficients on M gives me the symmetrized coefficients. And now my neural network, which is, again, one neural network per species on every atom, is going to take these coefficients and learn what is the energy that, or the energy correction that needs to be added to the underlying, the sum of all this total energy correction plus the total energy of the underlying energy functional should reproduce the reference energies. So basically my machine learning energy, the total machine learning energy is the sum of these atomic contributions, which are the outputs of these Wheeler-Parinello networks. And so that's the same written in here. And then, of course, as I say, I want to do not only obtain the energy up to there will be relatively simple, but I do want to have a potential, and I want to have the functional derivatives of my potential. So I can basically obtain this potential by taking the functional derivative of this energy, which of course depends on the density through the projections. And that, you develop this formula, is nothing else but the derivative of my machine learning network parameters with respect to the input coefficients, which are provided naturally in our libraries, machine learning libraries, times the orbitals themselves. These orbitals in here are not the underlying DFT orbitals. These are the projection orbitals. And so once you have that, you can add the final machine learning potential, you add it to the baseline to obtain the exact neural XC potential. So it's basically the machine learning, which is obtained from the previous derivatives times the coefficients times the base potential. And now you can do self-consistent calculations on here. Now, the way this is implemented, we have developed two different codes. So we have neural XC, which is written in Python, which basically deals with all the neural network optimization. Basically, you need to get the density from your DFT code. From the density, you get the description, build the neural network. It also is written so as it does the full machine learning loop. And then we have libnXC, which is written basically mimicking, and indeed is a plugin to libXC, which can be interfaced with any exchange, with any electronic structure code, takes these neural network models, and that basically adds to the underlying DFT potential, and so then you can do the full loop. Now, how we optimize? Because of course, what we want is to minimize the energy with respect to, so this is the loss function, these are the reference energies, these are the machine learning energies with respect to a density, which is the baseline density, but in reality, what our true loss should not be this, but should be basically the difference between the reference energies and the ground state density. And so how do we do with this? This is the so-called double optimization problem. And there are different ways of doing it. So the way we do it is basically we consider our density fixed during the optimization of the parameter. Omega here is just all the parameters of the neural network. We consider this rho fixed during the optimization of omega. Then we recompute the density. So basically, we find rho. We freeze that. We add a layer. We retrain the network. These next layers are frozen. We retrain the network, so on and so forth, until convergence is achieved. So this is called iterative train. And all this is described in our publications. So how does it work? Well, I'm going to go quickly through results, because I still want to go to the next model. But basically, what we're going to look is at two things. First is the transferability of our method, meaning that, as I say, we are training with a specific set of data for specific species and molecules, but we want to see how does it generalize for systems that it hasn't been, have not been trained on. And then we also want to look at performance in condensed systems, in particular in water. So again, for us, water is sort of the test system, the ultimate test system to evaluate how good are all these approximations. So what you see here is the errors of this functional when we train on a very small set. So this is 50 ethane samples and 20 propane samples. So that means 50 different configurations of ethane and 20 configurations of propane, all obtained at the coupled cluster there from the ML data set. And what we are looking at is how does it perform on molecules, on butane and isobutane molecules that basically were not used in the training set. And you see here, so the error, the mean absolute error is 6.6 MeV. So this is basically this number in here. If you compare to what are the errors for the baseline functional, by the way, is PBE, and these are the errors that will be obtained with other functionals, even if hybrid functionals. So we are very much within the chemical accuracy limit. Basically, that's what I'm marking here. This is my chemical accuracy, very close to this, which is a machine learned model for adding correlations in the wave function by the Miller group. Now, if you do the same, but you want to generalize to systems, ethylene, acetylene, propylene, where actually you have chemistries that were not in your fitting test, now you start seeing deviations. The errors are still very good, but definitely you start seeing deviations. So that means you have double bonds and you haven't trained to double bonds. Well, that's not going to describe very well double bonds. It improves definitely over PBE, but it's not going to give you the accuracy that you want. Well, you can correct this by adding more systems with the right chemistry. So how about for water? Remember that what we did before for water actually was was a lot of building because we've optimized an exchange, but then we added a monomer correction. And so here we are just training these atom center neural XC functionals, and we are going to use still the same data that we used for before, actually a little bit smaller set than the one before. So we have 400 monomers, 500 dimers, 250 trimers, and we are not looking at the errors on only those systems, but really on the condensed phase. So again, you see that you obtain a functional that, as compared to, this is a hybrid functional scan in PV, is really much better. And when you look at the actual performance of molecular dynamic simulation, now we are at the same level of MV-pol without any extra correction. And remember that MV-pol is basically giving us what we will call chemical accuracy. So you want to get a functional that works for the system that you are studying, you can do that. It's, of course, I mean, I will say that is a lot of work in a way. You want to train a functional to get some DFT description of your model that then you, in principle, want to be able to use beyond the system that you tested for. We did show that actually it is very extrapolable and it has a very large transferability. We didn't train for any broken bond configuration, and yet the protonation transfer for the water hexamer, which, as I say, is very hard, this energy barrier. We didn't fit to any energy barrier, by the way. It's very hard to describe, and yet the functional reproduces the level of coupled clusters. So it does have extrapolation beyond what it was fitted to, but I will say that there's still deficiencies. I just don't wanna go without saying that other related methods. So deep Hartree fog was developed soon after our method, and it's very, very similar in spirit to what we do, with the difference that what they, instead of looking at the real space density, they look at the density matrix still projected onto atom center basis. There's OrbNet, and then there's this MNC DFT. And this one actually is an interesting one. They took neural XC, and then they used in multi-configurational functional development, basically how to add extra corrections to using atom center functions like ours in MP2 and beyond MP2. Okay, so there are challenges. The first one is that there's no doubt that is expensive in training data. I mean, this might not sound like much, but we really would like to have something that we can optimize with a much reduced set of data. And that, basically what I showed you is the data that you need to be in a very narrow space. If we want to reach universality, we will need a much, much large amount of data. But I think the most important challenge and deficiency is that we are not using any information contained in the reference electron densities, and so we know nothing whether this functional is actually, what is it doing to the densities? Is it taking them closer to the exact density or farther away? And we know that has been pointed out to be a deficiency of empirically generated functionals, might actually be bringing us closer to the exact energy, but really not to the density. So when you look at how we do, and this is just for the moments of the charge density distribution, we did improve with respect to PVE a little bit, but this is comparing densities between our changes in density on going from PVE to coupled cluster, and changes on density on going from PVE to NXC. The reason we are doing this is actually, this was all developed for zero potential methods. Indeed, we did this all within Siesta. It can be used with quantum espresso and with CP2K, but it's a little bit complicated the way we did it. It's not complicated. Like, one needs to take into account the role of the zero potentials on this density definition. So how do we do? How we go beyond here and we go towards the sad potential? So one way is you can actually impose that the exact potential is reproduced. So if you have the exact density, you can invert this Schrodinger equation, obtain the reference exact potential, and then impose that our machine learned potential, which as we saw is basically just given by the derivatives of the function, the parameters of the neural network times the orbitals, that this and the reference one basically match. Problem of this is expensive, not in this method, but basically on calculating these reference potentials. It does work. So you look at the water molecule, if you impose, the hydrogen molecule, if you impose that the exact potential is reproduced, then the density is very much improved. This is versus PV, and this is with our fitted method. But that, I don't think that is the right way to go beyond here. So we actually stopped there. We're still working, and there are a lot of perspectives on this method. First of all is that, of course, one could go up in this, one can think of these neural XC potentials, so atom center potentials, and not only project the density, but project gradients of the density and project the Laplacian of the density, so going up the Jacob's ladder, so increasing this non-locality, going up the neural XC ladder. But there are other ways to do that, and that's bringing us back to the first where I started, which is how can we do to go and optimizing a functional on the actual grid, using functions that we somehow physically understand much better. And so basically it can be done, was shown, the first work on showing that this can be done was by the group of Kierenberg, where they found that one can use the equations, the constant equations, as a regularizer to optimize not only the energy, but also the density in the functional. So if we write our self-consistent loop of our electronic structure code in differentiable programming, we can basically prove the response function of the output, whatever it is, with respect to any input and any of the internal parameters. And that automatically opens the door to have gradient optimization, which before we didn't have. So what we are going to do is that we are going to optimize, in this case we are moving back, remember when I started, so now we are in the grid, we have a functional, this is my constant equation with my exchange correlation potential, which now at every point in the grid I'm going to make it dependent on the density, the gradient, the kinetic energy density, and of a set of parameters which are going to be my neural network. So my neural network is now basically on the grid. And so I can do this because I can run my self-consistent loop in here, and I can then go backwards, forward, backwards in this loop, and obtain the derivatives of each of the stages, each of the steps of my self-consistent. So what I'm showing in here is basically now my loss function is going to be coupled to everything that happens within my self-consistent loop. Not only that, I can write a loss function which depends on the energy, so errors in the energy, but also errors in the density. So there are two parts in here. So first, the composition of my loss function, but in addition to that, my loss function is going to be written as a sum of all these errors through all my self-consistent cycle, which I want to minimize, which naturally acts as a regularizer to obtain a converging self-consistent potential.
Right.
Yes.
So you propagate through the entire...
Through the entire loop, yes.
Isn't that too memory?
Okay, so yes, it is. So it is very memory expensive. Let me tell you, so there are lots of tricks. So first of all, we impose a loss function that favors the very reduced number of steps. So as we optimize, we decrease the number of steps in the self-consistent steps. And the second, we use symmetrized grids, so the molecules that I'm going in here. So the systems that we choose to optimize are these atomization energies and densities. They are basically on spherical atoms, so we can impose a spherical symmetry on the grid. So that is very simple. Same of ionization potential. For the barrier heights, we choose reactions that involve linear molecules, and we can impose cylindrical geometry and then atomic energies. So that's what I'm going to present is all with that. Now, actually, it becomes much more memory efficient if on this processing here, you basically use density fitting. The moment you use density fitting, then you just need the parameters for one of your self-consistent steps. And so that we have implemented now, and now we can go to any geometry. So basically, what we did is basically we rewrote the self-consistency loop by SCF, which, by the way, is all available in our GitHub, so you can get it and play and use it for, I mean, you can repeat all what I'm showing in here. So only for the self-consistency part, we haven't touched any part with respect to the basis, so the building of the Hamiltonian, but for everything else, it's all differentiable now. Okay, and the other thing which is important is that we actually, now we're gonna split the functional into exchange and correlation. So remember my first part where I said I only do exchange and I keep everything fixed? What I'm going to do now is have two different models, one for exchange, one for correlation, and I'm gonna do that in order to follow exact constraints. These are my original variables, so the density, the spin polarization, the reduced density gradient, and the kinetic energy, well, tau, basically, which is related to the kinetic energy density. The first thing that we do is, of course, we do a transformation because we want to have a reduced, basically, concentrate all our data within a reduced bounds. And these transformations have two purposes. One that, of course, we have now, similar to working on KF and KG, now we are working in a reduced length, if you want, and data set. But also, it acts as a regularizer, and it already imposed constraints for the functional derivatives at s equals 0. So very quickly, I'll show you, this is the exchange, this is the correlation, and in color in here are how the different constraints are imposed. So our exchange, at the end of the day, what we are doing is basically having an enhancement factor. These X2 bar and X3 bars are basically the transform, the ones that I define in here, so the ones that transform through the logarithmic filter. So the spin scaling and uniform density scaling of the exchange basically is shown in here, and the way we do it is just we are going to make it dependent on X2, which was the reduced density gradient, and X3, which is the tau, everything that depends on the kinetic energy density. So in a way, actually in exchange, I'm going back to where I was before. I'm actually making my exchange depending only on the reduced density gradient for alpha equal to 1, and then for alpha be different from 1, basically that's my meta GGA part. Now the homogeneous electron gas limit is imposed basically taking this function in here, this hyperbolic tangent of these two variables, and the local epochs for bound and non-negativity basically is imposed by taking this function I. So this in here impose my exact local Libox for bound. Taking A is basically that's 0.74. That will be my local Libox for bound, and then the non-negativity of the correlation function is basically taking I of 2. So with all these, there are not very large number of constraints, but we found that without these constraints, again, the functional can actually deviate very much from physical behavior. And this indeed favors the convergence to a much more accurate representation of the model. So let me just show you very, very quickly. I'll go quick through here. So these are the enhancement factors, which these are chosen for alpha equal to 1. So this will be your, let's say, your exchange part. And that's how it changed with respect to the baseline, which, okay, you have it in here. Our baseline, we start from a scan, by the way. In here, this optimization, but it's compared with all the other models. So it does actually give you a very homogeneous exchange enhancement factor. And now how it performs. So we're going to look at 3 different measurements. One is the energy. So these are GGA functionals, these are meta GGA functionals, and these are hybrid functionals. That's where we are. This is tested against a set, which I showed in here, which has a very large variety of properties. So it has evaluates covalent, non-covalent interaction, barrier energies, atomization energies, so you have the non-covalent for large and smaller systems, and also the covalent interactions also for large and smaller systems. So that's, in terms of energy, well, I think expectedly we improve. We are slightly better than SCAN. SCAN is a highly constrained functional. I'm done. This is basically it. If you look at the densities are again, very much improved. And it's nice to see this plot. So here I'm plotting the errors in the energy versus the errors in the density. And this is where all the functionals fall. So this is where you want to be, small errors in both. Of course, all the hybrid functionals are in that region. This is where we are. In a way, we kind of are at the interface of the meta-GGAs with hybrids, even though we are still a meta-GGA. You can define a metric that combines the two of them. You can ask me about it, so it's not very complex. In this combined metric, we are very much at the hybrid level. Now, I don't want to finish without talking or mentioning at least the DeepMind work, which came soon after our work. They did something very similar. They actually have they optimize and exchange correlation functional also on the grid. Basically, you have a neural network that takes density gradients, so on and so forth. It has an additional parameter. It's a local range-separated hybrid, which means they need the exchange and the exact exchange energy in the grid, which makes it actually very expensive. And what they did very smartly is that they didn't impose any constraints on the inputs to their neural network. Instead, their constraints is what I call it exchange constraints in the data. They impose, satisfy the fractional electron density and fractional spin density scaling. That's imposed exactly, which allows them then to describe very nicely heterogeneous, homogeneous covalent bond cleavage. So, I mean, the functional is really good. It improves very much over hybrids. Of course, it's an expensive functional. It's a range-separated hybrid. I think it's not there yet in that still the errors are relatively large. We've been using it. It's expensive, but it actually provides a very nice set to continue optimizing the methods. I will say that we need to extend to testing solid systems. You probably can ask, how does it perform for solids? And the answer is actually neither the Google one, neither ours improves very much in solids. So, because it's fitted to molecules. And indeed, the enhancement factor for solids requires certain changes that are actually not somehow seen when one optimizes only for molecules. So we will need to impose fitting also to solids. I would like to finish with a note, which is I think we've done a lot. This artificial intelligence has brought in very few years to where we were with the development of functionals, and we have already, what I would say, human intelligence has achieved in 50 years of functional development. I think what we are missing yet is having more accurate data, and it's probably that it's not yet clear whether just using these grid-based functionals is the way to go. Probably something more the way I presented in Atom Center, where you can actually incorporate many varied effects in a much more out-of-the-box way, might be the right way to go. So with this, I would like to thank you.